Hi everybody, welcome to Lecture 8 of Electrical Engineering 331. In this lecture, we will continue our discussion of finding the impulse response, and we will also talk about the step response and the ramp response. So you will recall that at the end of Lecture 7, we were learning a technique for finding the impulse response of a system that had input-output equation that looks like this. And we went ahead, we talked about that technique, we learned the steps, and we also worked an example problem and found that for that example problem that it did indeed work to give us the correct impulse response. However, we did not spend much time trying to gain any insight into the method. In other words, we didn't try to understand why one might expect that technique to work. And so that's what I want to do at the beginning of Lecture 8, is to sort of backtrack and try to gain a little more insight into that technique and understand better why we would suspect that it might work. Now, one more note before we jump into this. You might recall that in that technique in Lecture 7, we had a step 0 that applied for the case where these first two terms don't exist. In other words, where alpha 2 is equal to alpha 1 is equal to 0. And we saw that in that case that the impulse response drops out immediately. So in this discussion here, we're not interested in that very simple case. We're interested in the case where you have to go through all of the steps, and we want to understand why that works. So for this discussion, assume that at least one of those coefficients is non-zero. Okay, so let's jump into this and see what we can do. Now remember, once again then, what we're trying to do is to find the impulse response of a system that has this input-output equation. And just to remind you, the impulse response is designated as h of t, and h of t is the value of the output then when the input is equal to the impulse, or the delta function. So that means that we can substitute in h for y if we also substitute the delta function for x. So this is the equation that h satisfies right here, and we want to find what h is. Okay? So what we're going to do to begin with is the following. You know, this right-hand side here is a little bit complicated. We would like it better if this was simpler. So we're going to go back to this original system equation, and instead of considering a system that has this system equation, what we're going to do is look at an associated system that has this equation down here. Now notice that this associated system has an input-output equation that is exactly the same on the left-hand side. That's exactly the same. But the difference is that instead of having this complicated looking expression here on the right hand side, beta 1 dx dt plus beta naught x of t, all we have is x of t down here for this associated system. Okay, so we're going to look at this associated system first, and then our idea is that maybe we can find, if we can find the impulse response of this simpler associated system, then from that maybe we could find the impulse response of the system that we're really interested in, which is the one that has this input-output equation. So for this simpler, or associated system, whichever you want to call it, let's call the impulse response of this system h hat of t. We don't want to call it h of t because then it's easy to confuse that with the overall h of t for the original system, and of course that's not the case. We're going to find h hat of t, which is the impulse response of this system, first, and then from there we will try to find the h of t for this system. So, okay, so again, h hat of t is the impulse response of this system. So, what we're going to do is, first of all, think about, well, if we could find that h hat of t, if we could, then how could we find h of t for the overall system? Well, again, look at the system equation for the associated system and the original system. We see that the two equations are exactly the same on the left-hand side, but on the right-hand side, where we have x of t for the simple or associated system, we have beta 1 dx dt plus beta naught x of t in the original system. So this leads us to believe or to suspect that maybe if we found h hat for this system, the impulse response for this system, then the impulse response for the overall system would simply be beta 1 dh hat dt plus beta naught h hat of t. In other words, since the right-hand side up here is beta 1 times the derivative of this right-hand side plus beta naught times the right-hand side, then we're thinking that the impulse responses would be related in exactly the same way, that the impulse response of this system would just be beta 1 times the derivative of the impulse response down here plus beta naught times the impulse response down here. So just notice we're doing the same thing for the relationship between h and h hat as we have between the original right-hand side and the new right-hand side. That's our thinking. And so we will, I'm certainly not giving you any kind of a rigorous mathematical proof that that is true, but we would strongly suspect that this might be true, and so let's investigate and see what happens. So if this is true, then that says that, of course, this is a simple operation here. This is just taking the derivative, multiplying by beta 1, then taking the function h hat, multiplying by beta naught, and adding that all together. It's always easy to take the derivative of a function. So if this is true, then it's going to be easy for us to find h from h hat. But now let's see how we would find h hat. Now remember, h hat is the impulse response for the simpler associated system, okay? And that's what we're saying right here. H hat is the impulse response of this simpler associated system. Okay? Well, that means then that if we plug in h hat for y and delta for x, then h hat is the solution of this equation right here. Now, how do we find h hat? Well, the first thing we do is we find the homogeneous solution, yh of t. In other words, that's the solution of the homogeneous equation, the equation that we get when we drop this stuff on the right-hand side and replace it by 0. Now, that may seem like a strange thing to do. Why would we want to drop the right-hand side and set it equal to 0? But if you think about it for a moment, that's not such a strange thing to do, because remember what the delta function itself looks like. The delta function is equal to 0 for all t greater than 0. So we would expect then that maybe for all those t's greater than 0, since this top equation is actually, it becomes the second equation when t is greater than 0, the right-hand sides both become 0. So we would expect that maybe for t greater than 0, that h hat of t is equal to that homogeneous solution. And furthermore, remember that coming back up here and looking at this again, that delta of t is equal to 0 for all t less than 0 as well. So that means that the system has had no input, because remember, this is the input-output equation here. The the right-hand side is the input, and the left-hand side tells us how the output is related to that input. And so if the input, which in this case is just plain delta of t, if it's equal to 0 for all t less than 0, then if this is, as long as this is what was called a causal system, we expect this system has no output until t equals 0, because we don't have any input until t equals 0. And therefore, we would expect h hat of t to be 0 for all t less than 0. So if h hat is equal to 0 for all t less than 0, and is equal to yh of t for all t greater than 0, that's what we have right here. We're suspecting that h hat of t is equal to 0 for all t less than 0, and yh of t for all t greater than 0. Well, then that explains why in our procedure we learned in lecture 7, we said that we're going to try h hat of t is equal to yh of t times u of t, because that would have exactly this value. It would be equal to 0 for all t less than 0, but it would be equal to yh of t for all t greater than 0. So that's what we're going to try, and of course, as you probably suspect, this does indeed work. And so that's it. That is our method. So that explains our method. Just to review then, what we do is we find the homogeneous solution, we multiply it by u of t to get h hat, then we find the unknown constants in h hat of t by plugging it into the system equation, the input-output equation for the associated system, and then finally we get h of t from h hat of t by this formula right here. So that's it. That's what the technique, that's the technique in a nutshell. So I want to look at one more example of how this works. You know, the example we did in lecture 7. Okay, we did an example in lecture 7, and then we also had a problem 4 in test 7. So let's do one more example now. The example in lecture 7 was rather lengthy, whereas the problem 4 from test 7 was pretty short. So this one is sort of in between. So let's look at the example. What we want to do this time is say we want to look at the system that has the input-output equation d squared y dt squared plus 4y of t is equal to 2 dx dt plus 4x of t. Now remember, what we're interested in doing first is looking at the homogeneous equation, where we have d squared y dt squared plus 4y of t is equal to 0. That's that homogeneous equation. Now, going back to one of our earlier lectures where we looked at the solution of homogeneous equations, we know that what we should do is propose a solution of the form CE to the PT. And when we do that, in this case, then the d squared y dt squared would give us p squared plus, then we have this 4. So p squared plus 4 is equal to 0, which tells us that this should be p squared here. P squared is equal to negative 4. Actually, let me fix that real quick. Just for the sake of accuracy. I mean, I think it's pretty clear, but just like to be sure we're all together on this. There we go. So now it's correct. P squared is equal to -4. And so when we take the square root of both sides, we get P equals plus or minus 2j. Remember, j is the square root of -1. Okay. And so we said before when we did our review of differential equations that in this case you could write the two homogeneous solutions if you wish. You could write it as C1 e to the positive 2jt plus C2 e to the minus 2jt. You could write it that way, but equivalently you could write it as C1 sine 2t plus C2 cosine 2t. And that, in the problems that we'll be working in this course, that will usually be the better way to do things, the more efficient way to do things. And so that's what I've done right here. We have YH of t is equal to C1 sine 2t plus C2 cosine 2t. Now remember then, after you get the homogeneous solution, the next step in the technique is to set H hat equal to the homogeneous solution multiplied by U of t. And so that's what we have done right here. And then we want to find those constants. And we find those constants by substituting H hat of t back into the system equation, but it's not quite this system equation, it's the system equation for the associated system, where we replace all this stuff on the right-hand side simply by x of t. And then, of course, when we substitute h of t into the equation, that x of t, since h hat of t, when we substitute h hat of t into the equation on the left-hand side, and we use x of t on the right-hand side for the associated system, that x of t will then become delta of t. So, and just to review, just to make sure you understand what I mean there, I'm talking about this right here, this equation. So we've substituted h hat everywhere on the left-hand side, and on the right-hand side we have delta of t. So that's what I mean. That's the equation that allows us to find those unknown coefficients in h hat. So that's what we're going to do. You can see that here's our h hat right here, and we substitute that into this equation, but putting delta of t on the right-hand side. So there's the delta of t on the right-hand side, right there. Instead of 2dx dt plus 4x of t, we have delta of t on the right-hand side. And on the left-hand side, what we have done is just substituted h hat in for y up here. So we have d squared dt squared of h hat. Here's h hat, so we're sticking that in there, plus 4h hat. So there's plus 4h hat. And we start turning the crank. Now, I want to be careful and look at this step by step. Okay, so I'm going to write this second derivative as the derivative of the first derivative. So I'm going to keep one derivative outside, and I'm going to go ahead and take the first derivative of what's left in here. Now, each one of these is a product, and so we're going to have to do this carefully. Now notice the first term is we have C1 sine 2t times delta of t, and that's coming in because we have the first term, we're considering C1 sine 2t to be the first term, and u of t to be the second term. So this represents the first times the derivative of the second, and then this represents the second times the derivative of the first. And then the same thing here for this second term. We have we're going to consider C2 cosine 2t to be the first term and u of t to be the second term. So we have the first times the derivative of the second plus the second times the derivative of the first. And then everything else is pretty much just automatic. We bring down this 4, we go ahead and multiply it by everything in here, so we get 4c1 sine 2t u of t plus 4c2 cosine 2t u of t, and we bring down the delta of t. Now I want to call your attention to something here. Remember we said that whenever you have an expression of the form f of t times delta of t, you go ahead and immediately simplify it to f of 0 times delta of t. And we have two expressions that pop up that look like that. We have a sine 2t delta of t here and a cosine 2t delta of t here. Well, that sine 2t delta, or actually c1 sine 2t delta of t, since here f of t is sine 2t, so f of 0 is sine of 2 times 0, and the sine of 2 times 0 is the sine of 0, which is 0. So this term actually goes away. But on the other hand, over here we have c2 cosine 2t delta of t. So in this case, c2 cosine 2t is playing the role of f of t. And so f of 0 would be c2 times the cosine of 0, or just c2. So this term becomes c2 delta of t. And it really is helpful when you go through this procedure. It really will be helpful if every time a term pops up with delta of t that looks like that, if you go ahead and simplify it right away, as we've done here. So, now that I have done that, I'm ready to go ahead and take take one, this was two derivatives up here, so I'm ready to take one more derivative. So since this is 0, we don't have to take a derivative there. When we take the derivative of 2c1 cosine 2t u of t, again, we're going to have to use the product rule. So we'll get the first times the derivative of the second, plus the second times the derivative of the first. That's right there. And then we also have to take a derivative of this c2 delta of t, and that gives us c2 delta dot of t. And then finally, we have one more product here, so we have to use the product rule when we take the derivative of that, and we'll get the first times the derivative of the second, and the second times the derivative of the first. And then everything else just comes down exactly as it is in the previous equation. And you will notice that once again we're coming up with two terms here that have the form f of t times delta of t. In the first case, f of t is equal to c1 sine 2t, and so f of 0 is 0, so that goes away. And in the second case, let's see, I'm sorry, I skipped back to what we had done before. We should be looking at here. So in the right here, in this first case, f of t is 2c1 cosine of 2t. And so when we evaluate that at t equals 0, that's 2c1 cosine of 0, or just 2c1. So this becomes 2c1 delta of t. And down here, negative 2c2 sine 2t is playing the role of f of t. So f of 0 would be negative 2c2 sine of 0, which is 0. So this goes away. And therefore, if we bring everything down here, we get this. Oh, and remember, this is the point where we said in lecture 7, it was at this point, right before the end, where you find the c's. This is where you expect cancellation to occur, and so we're going to be looking for that. But bringing everything down, okay, we have 2c1 delta of t. Now the next term is minus 4c1 sine 2t u of t, but that cancels with this positive 4c1 sine 2t u of t. So there's our first example of cancellation. Then we have c2 delta dot of t. We bring that down. This term is 0, so we don't have to worry about it. The next term is minus 4c2 cosine 2t u of t, but that cancels this positive 4c2 cosine 2t u of t. So there's a second instance of cancellation. So so this is all that we have left on the left-hand side. And then on the right-hand side, we just have delta of t. So this turns out to be quite simple. 2c1 delta of t plus c2 delta dot of t is equal to delta of t. And remember, delta dot just represents d delta dt. And it's very easy to solve for the coefficients because there's no delta dot on the right-hand side, so C2 must be 0. And on the and as far as C1 is concerned, well, we have a 1 delta of t on the right, so we must have a 1 delta t on the left, and therefore 2C1 must be equal to 1, or C1 must be 1/2. So it's just that simple. We have C1 is 1/2, C2 is 0, and therefore plugging those two values back into our expression for h hat of t, which is right up here, we get h hat of t is equal to 1/2 sine of 2t u of t. And remember now, that's the impulse response for the simple associated system. And to get the impulse response of the overall system, now we just say 2 dh hat dt plus 4 h hat of t. And so we do that right here. And once again, we'll get a little simplification. When we take the derivative, we have to take the derivative of a product, so we'll have to use the product rule again. But I think everything else here is straightforward, and we end up with this expression, that the impulse response of the original system is 2 cosine 2t u of t plus 2 sine 2t u of t. And now, just to make sure that that is correct, we can plug that in for y of t in the original input-output equation, and plug in delta of t for x of t in that same equation. And if we do that, we would get this. And I'll just scroll up. I won't take up your time checking all of that, because it really is just turning the crank, but I will leave it up there on the screen so that you can see it or take a picture of it. But you will see that sure enough, it does turn out to be exactly the same thing. So this technique has again yielded us the correct impulse response for a system. This time, I hope that maybe you get a little more insight into why we would expect this technique to work. So that's all for finding the impulse response. And what we want to do now is look at a couple of examples for why the impulse response is so important. You might remember that I said at the beginning of Lecture 7 that the impulse response was very important, that it really tells you all you need to know about a system. And so now I want to begin to justify that statement to help you understand just how helpful it is to know about the impulse response. So the rest of this lecture and the next lecture as well will help us to see why the impulse response of a system is so important. Okay? Now, the remaining two ideas that we're going to talk about in this lecture are called the step response and the ramp response. And so let's jump right into this and look first at the step response. The step response of a system is designated in your book as y sub step of t, and it's simply the response of the system to the step function, as you would expect. So when you put, just like the impulse response is going to be the output when the input is the impulse function, well, the step response is the output when the input is the step function, u of t. And that's what we say here. In other words, y step of t is the output when the input is the step function, u of t. How can we find the step response? Well, fortunately, of course, we've just been talking about a whole procedure for finding the impulse impulse response, well, we're not going to have to find a new procedure now, or at least not any kind of a complicated procedure for finding the step response. In fact, it's very, very easy. So this is the way it goes. Remember now that h of t is the response to delta of t. And also recall that we learned that the unit step function is the integral of delta of t. So if the unit step is the integral of delta of t, then the response to the unit step is the integral of the response to delta of t. Let me say that one more time because it's such an interesting idea. The unit step is the integral of the impulse. So the response to the unit step is the integral of the response to the impulse. It's just that simple. So we have here y step of t is the integral from negative infinity to t of h of tau d tau, which is equivalent to saying, if you take the derivative of both sides, it's equivalent to saying that h of t is dy step dt. So the knowledge of the impulse response allows us to immediately find the unit step response. Let's look at an example of this and see how it works. Okay, in problem 4 of test 7, we found that the impulse response of the system having this input-output equation right here is h of t is equal to delta of t minus 6e to the negative 3t u of t. We found that using the technique learned in lecture 7 and reviewed above here at the beginning of lecture 8. So now, suppose that for this system that has this input-output equation, suppose that we don't want the impulse response, but we want the unit step response. Okay, well, in other words, just to make sure it's clear, we want to find the function y step of t that could take the place of y when for x we plug in u. Now notice, okay, we've plugged in y step for y, so we get dy step dt plus 3y step. But notice here, when I plug in u for x, I'm going ahead and taking into account the fact that du dt is delta of t. So that's why I have this delta of t there. But then minus 3x just becomes minus 3u, because again, I'm just plugging in u for x. So how do we find this? Well, what we do is use the technique we've just learned about. We say that, okay, this, we've already learned from previous work that this is the response to the impulse. So the response to the unit step is just the integral of this. So that's what we have right down here. We say y step of t is the integral of negative infinity to t of this function right here. So we have delta of tau minus 6e to the negative 3 tau u of tau d tau. Okay, now I'm going to go over this, the rest of this very carefully, because these integrals of this type can be a little tricky to evaluate. So I want you to follow through step by step. Okay. Well, the first thing we'll do is go ahead, since we have two terms here in the integral, we're going to go ahead and split this up into two integrals. So we'll have an integral from negative infinity to t of delta of tau d tau minus 6 times the integral from negative infinity to t of e to the minus 3 tau u of, that should be tau right there. Let me get that fixed. Just a second here. Probably sometimes seems like I'm a stickler on this stuff, but I think it pays to be really careful. So let's see here. There we go. So now it's tau in there as it should be. Okay, so again, we've split this up. Here's the first thing we get, and then -6 integral minus infinity to t of e to the -3 tau u of tau d tau. Okay, now fortunately the first integral is very easy. We already know that the integral of the delta function from -infinity to t is u of t. But it's the second one that's a little bit tricky, so we're going to do this very carefully. So the -6 I bring out here in front, and then I'm going to have a bracket because I need to evaluate this integral for two different cases. I'm going to evaluate the integral when t is less than 0, and also evaluate it when t is greater than 0. Now let's think about how this goes. When t is less than 0, that means that the upper limit of the integral is less than 0. So we're integrating from -infinity up to some other negative number. We never do get to 0. Tau is always in the negative range. And in the in the integrand here, we have u of tau. And u of tau never becomes non-zero until tau gets into the positive range. So if tau is always negative, then u of tau is always 0, and therefore the integral is just completely vanishes. It's just 0. So if t is a negative number, again, then that means that the whole range of integration is over negative values of tau, where this u function is always equal to 0, so we get no contribution from the integral at all. So that's why I write down here 0 if t is less than 0. Okay, now what if t is greater than 0? Okay, well, if t is greater than 0, then we're going to have to take into account what's going on. But notice one other interesting thing. The lower limit, instead of being -infinity, it can be replaced by 0. Why is that? Well, it's related to what we said just a moment ago. We don't have to consider the case where tau is less than 0. Because whenever tau is less than 0, u is equal to 0, and so the integral vanishes. So instead of starting all the way back at -infinity, we can start at tau equals 0. And then we integrate up to tau equals t. Because remember, now in this second case, we're considering the case t is greater than 0. And one last thing, notice that not only can we change that lower limit on the integral, but we can do one more thing. If we're now only integrating over the positive values of t, well, we know that when tau, I should just say positive values of tau. If we're only integrating over the positive values of tau, well, we know that when tau is a positive number, what is u of tau? It's just plain old 1. So we don't even have to write it down. So that's how we have simplified this integral into this expression right here. That is important for you to be able to do if you want to solve integrals like this completely in the integral expression. Now we're gonna talk a little bit later about a graphical method for evaluating some of these integrals, but it's very nice to know how to do what I just did there. It can save you time, and it can also give you a checking procedure if you do want to do the graphical method. So we'll look at another example of this before this lecture is over, but that's how this goes. Okay, so now continuing, the rest of this problem is very simple. The u of t comes down, the minus 6 comes down, the first line up here comes down, and we're ready to go ahead and evaluate this integral. It almost has the form e to the u du, but we need a negative 3 on the inside of the integral, and so a negative 1/3 on the outside of the integral. So this is negative 1/3 e to the minus 3 tau evaluated from 0 to t if t is greater than 0. And so then bringing things down, and e to the minus 3 tau evaluated at tau equals t, because just becomes e to the minus 3t. And at the lower limit, when we subtract the value at the lower limit, e to the 0 is just 1. So that's what we've done there. And now notice what I do here now. Okay, u of t comes down, the minus 6 comes down, and then I have rewritten this expression right here as minus 1/3 e to the minus 3t times minus 1 times u of t. And just think about that for a moment and make sure you understand why this expression is the same thing as this expression. Because down here, this expression, when t is less than 0, u of t is 0 and it just goes away, so I would get that. But on the other hand, when t is greater than 0, I would get, this is equal to 1, and so I would get minus 1/3 e to the minus 3t minus 1, which is that. So that's why I can make that substitution. And now finally then, the u of t comes down. Minus 6 times minus 1/3 is positive 2. I'll leave this in brackets for the moment and bring down the u of t. And then finally, let's see, notice that we have right here, we have a minus 2 u of t here, 2 times minus 1 times u of t. So a minus 2 u of t here and a u of t there, so that gives me minus u of t. And I also have a 2 e to the minus 3t u of t, which I've brought down right there, and that's it. That's the end of it, and this should be the step response of that system. And so now to check it, if you want to go through the checking procedure, what you do is come back up here. Remember, we said up here that y step is the solution to this equation right here. And so I checked it, I plugged into that equation to check and see if it worked. And you see it actually doesn't take too terribly long, and it did indeed work. Here on the left hand side I have 2 delta of t minus delta of t, which becomes just delta of t minus 3 u of t, so the two sides are exactly equal. And so that's how we find the step response of a system. And now the last thing to talk about in this lecture is how do we find the ramp response, and it is extremely similar. Okay, so the ramp response of a system is designated in your book as y ramp of t, and as the name suggests, that is the response of the system. It's the output when the input is the ramp function. And so, and that's what we've said right here. How can we find the ramp response? Well, recall that y step of t is the response to the step function, and we also recall that r of t is the integral of the step function. So if r of t is the integral of the step function, then the response to r of t is the integral of the response to the step function. It's the same kind of reasoning we used above to find the step response, being, since the step is the integral of the impulse, the response to the step is the integral of the response to the impulse. Same kind of reasoning here. Since the ramp is the integral of the step, the response to the ramp is the integral of the response to the step. Just that simple. And this equation right here, if we took the derivative on both sides, it would say y step of t is dy ramp of t dt. So the knowledge of the step response allows us to immediately find the ramp response. And of course, we can get the step response if we know the impulse response. So that again is helping to emphasize how important the impulse response is. If we integrate it once, we get the step response. And then if we integrate the step response, we get the ramp response. Okay, so I want to do an example of this to conclude lecture 8. And the example I will do is a problem we did just above. Remember that this again refers to problem 4 on test 7. And in that case, we found the impulse response. And now just above, we found the step response to that system right here. And that's what we have repeated down here. So now if we integrate this one more time, we will find the ramp response. And again, that's just that means that if we put in the ramp function for x of t in the input-output equation, and put in y ramp for y, we get this. So I'm going to put 2 asterisks by that. And again, we expect now the way to get that is just all we have to do is integrate the step response one time. So let's see if it really does work that way. We say y ramp of t is the integral of the step response. And again, we're integrating from negative infinity to t. Just as before, we're going to break this up into 2 integrals. Just like before, we have one integral that's going to be a little bit complicated here that we'll break up into 2, we will express in a different way. And then the integral of u of tau d tau is from negative infinity to t is r of t. So the second part is easy, but we got to figure out what to do with this. And again, the way that I have broken this up, let's look at it again, just like we did before, because this is important to understand. In this integral, if t is less than 0, then we're only integrating over negative values of tau, from negative infinity to t. And if tau is always negative, then u of tau is always equal to 0, and the integral goes away completely. So if t is less than 0, we can just immediately say 0, and we don't have to worry. On the other hand, if t is greater than 0, the way we reason this is the following. We don't really have to integrate from negative infinity up to 0, because over those negative values of tau, again, u of tau is equal to 0, and that portion of the integral goes away. So we really only have to integrate from 0 up to t. Remember, this is the case t is positive. So we're going to integrate from 0 to t, and we have 2e to the minus 3 tau. And again, since we're only integrating over the positive values of tau, whenever tau is positive, u of tau is 1, so we don't even have to write that down. Okay? And then bringing this down, e to the minus 3t, in order to integrate this, we're going to put a negative 3 on the inside and negative 1/3 on the outside. So we have, and don't forget this too, so we have negative 2/3 e to the minus 3 tau from 0 to t. If t is greater than 0, 0. If t is less than 0, minus r of t. And coming on down, this becomes, when we integrate this, we will get, and evaluate it, we're going to get minus 2/3 e to the minus 3t minus 1 if t is greater than 0, 0 if t is less than 0. And just like before, we now will take this bracketed expression and write it as a formula. And we just have this u of t to express the fact that we're going to get 0 if t is less than 0, but we get this if t is greater than 0. And notice that that is identical to this. And then we bring down the minus r of t. And then when we multiply everything out here, we get minus 2/3 e to the minus 3t u of t plus 2/3 u of t minus r of t. And that is the ramp response of this system. And if you wish to check that, then you will just plug that back in to this equation with the 2 stars right there. And that's what I've done down here. And again, it really doesn't take too much effort to turn the crank and verify. If we get down to this point right here and notice that we have a minus 2/3 delta of t there and a plus 2/3 delta of t there. So those, well, here I've brought it down. So minus 2/3 delta of t is from there. That comes there. The 2e to the minus 3t u of t cancels with the minus 2e to the minus 3t u of t, so we don't have to worry about that. Then 2/3 delta of t comes down right here. Minus u of t comes down right here. And this plus 2u of t comes down here. Minus 3r of t comes down here. And the right-hand side I just bring down as it is. And then you see that minus 2/3 delta of t cancels with 2/3 delta of t. The minus u of t plus 2u of t becomes u of t. Minus 3r of t just comes down. And so we have u of t minus 3r of t equals question mark u of t minus 3r of t. And of course that is true. And so this technique seems to indeed work for finding the ramp response of a system. So that begins to give us a flavor of why the impulse response is so important. But we're going to learn in Lecture 7 that there's still a lot more importance about the impulse response when we look at use another technique of trying to find the response to an arbitrary input. And so we'll talk about that next time. But that concludes Lecture 8, and so good luck.